Bonjour et merci. I'm going to speak in English because my French is not wonderful, so I'm sorry. This afternoon I'm going to present some work that we've been doing looking at characterizing rainfall and erosion using a lake data set. So the lake that we're looking at predominantly to start with is a lake called Lake Arbou. It's located in the Midi-Pyrenees, and it's the very top lake in the catchment. There's no upstream deposition locations. It's got quite a small, nice, concise catchment. And we have a couple of late calls that come through here that have been analysed as part of this record. So to put it in context, it's obviously been dated, but we've also got records of anthropic contamination in the catchment, and we've got microcharcoals that have been through there, so that we can see that we've actually got some fire going through there, and predominantly increasing over the most recent record. And we've got two proxies that we've looked at to try and look at our erosion in this area. One of them is the red amorphous particles, and we can see that we've got a link through here with quite a lot of a record in the most recent period. And we've also got a rubidium that we've chosen as a record to look at our erosion through the section. And that's also increased in the amount of deposition that's happened in the most recent past. At a closer timescale, where we've actually got a rainfall record that we can compare things to, and we know how much rainfall has occurred, the number of events that have occurred through the period. We've got where are we? We've got our rainfall record, our average rainfall record going through. We can see what our humidity through that section is. We can also see there's a slight rise in temperature that's occurred over the recent past. And we know what our major and minor rainfall events that have occurred, so we can count how many have occurred during the record period slices of our LACUSTRINE core. We've also got indication of anthropic pollution going through, and we have some pollen data going through here. So we have a historic record back to about the 1800s of the types of vegetation and the amount of tree cover that we've got through this area. So what we're trying to do is take all of that and say, okay, we know the recent rainfall, we have an idea of how much deposition is in the lake that's come from the soil and the catchment. Can we use that to then identify how much erosion's actually occurred? Can we then use that to go backwards and identify the characterization of the rainfall that's happened? And therefore give us an idea of how the trends have changed over time, whether we're getting more rainfall events, less rainfall events, and things like that. So if we look at that as a cumulative rate, we can see theoretically, if it is only being driven by the total amount of rainfall we've got, then these should parallel quite nicely. So cumulatively, we've got an idea that, okay, so we have a continued increase in the amount of deposition that's going through that's relatively consistent with the amount of total rainfall we've got, but they're not perfect. So what we want to know is, why do we have these shifts here that aren't perfectly parallel? And is there a way that we can characterize what's going on? So we've used the deploy equation, which is a really, really simple erosion equation. Like, it's one of the most simple possible equations there is out there. So ES is a variable that gives us an indication of erosion susceptibility that is in the catchment that you're looking at. So if you know what your rainfall is, and you know all the rest of your catchment characteristics, and you have a record of the amount of deposition that there is inside your lake that's indicating the amount of erosion that's occurred off that catchment, you can calculate what your erosion susceptibility value is. The problem there is, if you go backwards in time, obviously you don't have a rainfall record, therefore calculating your erosion susceptibility value is quite difficult, so you have to find a proxy that's going to work through this. When Deploy created this equation, he used this as a constant. So the ES value is a constant in all research that's been, or use of it has been done up until now. And when you use it in the long term, rather than looking at individual events, the value that they use sits somewhere in here. So most of the analysis that's been done using this equation up until now has used that variable as a constant. However, erosion is not necessarily constant. If you shift the land use, if you shift the amount of rainfall that's going through there, the number of events that you have, the extreme events that happen, all the rest of this, then theoretically the susceptibility to erosion off that catchment should change. Sort of makes sense. So what we want to know is, firstly, can we identify what our ES value is going backwards? And can you use that ES value to identify the changes in erosion susceptibility in your catchment? Can you use that as an indicator of how much erosion has happened in the past, or at least how susceptible that catchment is to erosion in the past? Can you then look at that to identify what the deviation away from total rainfall with your amount of deposition in that lake has been? Can it help explain some of these things? So we've done some basic first checks. If you just use your proxy, so your red amorphous particle to start with, and you do a cumulative analysis, you can see that you've got your total cumulative rainfall that's gone through here, and it looks quite nice until you look at this. So when you only use your proxy, it doesn't necessarily give you a perfect indication of the total rainfall that's gone through there. It's good, it's close, but it doesn't give you the nuances of what's happening in the rainfall through the period. So we've looked at what the rainfall would be if we only used the proxy, the red amorphous proxy. We've looked at if knowing what the peaks, the number of peaks that we've had in that period would be, to try and calculate whether that would give us a better indication. And then we've also used the total deposition, so not just the soil deposition in your lake, to try and identify how much rainfall we would have. And you can see that it lands up being a bit better, but we still have outliers going through the section. If you look at rubidium, the other proxy that we're considering, when you look at the cumulative trends, of course it looks quite nice because it hides all of the nuances that are going on. But when you actually plot it compared to what you know should be happening, you land up with sort of a mess of data sets all over the place, and it doesn't land up giving you a nice clean indication of the amount of rainfall that's going through. And this is just total rainfall. It doesn't give you an indication of the total number of events or anything that's going through. So if you have no rainfall record, if you're not looking at the recent past, you're trying to actually go back through your LACUSTRINE record to try and calculate the amount of rainfall, how do you do that if you don't have an ES value that's static? If we do use our proxies, can our proxies be used to reconstruct this rainfall on a slightly more detailed level? And can you use the vegetation reconstruction to try and indicate the amount of rainfall that you have through there? And I'm going way too slowly. So what we've done is we've calculated our rainfall, and then we've gone through and used the proxies to calculate what our ES variable should be. When you calculate this using your proxy, so the amount of proxy that you've got plus your pollen model, you land up with a much better reconstruction through our known rainfall. If you do this then looking on a spatial level, so not just looking at our lake, but looking at over 10 lakes across the entire range of the Pyrenees, you land up finding that your standard VE calculation doesn't actually work very well when you do it spatially, unless you add in your ES proxy and your revised calculation of what that would be with time and space. And you land up with a much better idea of what your rainfall should theoretically be through here. If you do this with rubidium, you land up getting similar positive results through here and a better proxy through proxy indication through there. And if you do it spatially, again, you get a better result of synthesized rainfall for a period that you know. Okay, so we know that we can therefore calculate potentially the amount of rainfall within a period where we've actually got a record to calibrate it back to. But if we take that further back, can we try and calculate or represent the amount of rainfall that's happened in the past? So the black is the known rainfall, and this is using our RAP, our red amorphous particles, through here, and this is with the rubidium. And the orange and the green are using, well, the green's using the static ES value, and the orange is using a slightly less modified, uncalculated ES. But if we do recalculate our ES using our proxies, we land up with these blue values through here. And as you can see, they're actually quite well represented through this section, and they continue back to give us a moderately decent representation looking into the past of the amount of total rainfall that we've got. The rubidium doesn't work quite so well. This is partly due to the time steps. So the time step in the rubidium is sort of 2 to 3 years instead of the 10 years we've got for our RAP. But the general static, if you look at the dark blue, the static line through representation through here is within QE of what you would kind of hope to expect. However, you can also take your RAP and actually calculate the number of total rainfall events that have happened. So if you look at the major and minor rainfall events, and we've tentatively said that a minor event is something that's got sort of 30 millimetres per day in intensity, and a major event something that's more than 60, you can actually represent the amount of, or the number of major and minor rainfall events that are happening with known information, and then go back and potentially represent the amount of rainfall events that are occurring in the past. So now we don't just have a total rainfall representation or indication, but we've actually got a number of events that are happening. So just to finish that off, if you look at the ES proxy over time, you see that there is a shift in our EX proxy, and we've actually got a wobble or an increase in variation in the most recent periods. So this would suggest that since sort of about 1980, 1990, we've actually got a shift, and some of that is due to shifts in temperature, changes in rainfall, and snowmelt and things like that, that's actually modifying the susceptibility of the erosion that's happening in this catchment. Thank you.
Thank you for this methodological approach of the rainfall reconstitution at the scale of small catchment. Une question, deux questions. Oui.
Okay, so the initial catchment that we looked at, the Roux catchment, is small, very small. Sorry, that one's very small. But when we've done the, so yes, it's tiny. Yeah, yeah. But when we've done our spatial analysis, we're looking down here. Some of these catchments are enormous. Like we've got Paladru and Blanquehuet, which are very large lakes in very large catchments. They're not. So we've got 14 catchments in total, and they're across the Pyrenees, and they're not all the first lake at the top of the catchment. What's the size of Paladru or Blanquehuet's? I have it written, and it's not in this presentation. But yeah, we're talking like an order of magnitude twice larger than what this catchment would be. Wait. Cool.
Une autre dernière petite question. Non, pas joli. OK. Thank you.